diving into a project on vehicle detection. I'm Ankit Garg, and together with my teammates Rhythm Jagota and Aditya Kiran, we will be presenting to you our project on neural networks. So let's begin by the motivation of our project. So we are addressing the so the urban traffic congestion and vehicle detection is a pressing issue affecting countless individuals daily. Our project is guided by three primary objectives. Firstly, the urban traffic management. Secondly, the support for urban planning. Thirdly, the role of vehicle detection. Our project aims a comprehensive toolkit for traffic density analysis and vehicle detection, contributing to more traffic efficient traffic flow and enhancing urban living standards. Moving on to the data set, our project relies on curated data set of top view of vehicle images, comprising of 626 images, each annotated in YOLO V8 format. This data set offers an ideal training ground for our object detection models. Moving on to the baseline model, we selected faster RCNN as a baseline model for the task of vehicle detection, which is derived from TensorFlow model Z. It leverages a ResNet backbone trained on the dataset, recognized benchmark in an object detection algorithm. So we'll talk about firstly the basic object detection algorithm, which is the RCNN, before we move on to our baseline model, which is the faster RCNN. So talking about RCNN, it operates through a two-step approach. It first sifts through the entire image to identify areas where an object might be located. Then it zooms onto each marked area, scrutinizing them closely to determine whether they indeed contain that desired object or not. This two-step process ensures thorough coverage of the image while maintaining a high level of accuracy in object detection. Coming on to the improvement of that is the fast RCNN. It refines the RCNN methodology by incorporating entire image in the detection process. Instead of separately analyzing each marked area like RCNN, fast RCNN takes a holistic approach by considering the entire image at once. It efficiently gathers from the entire screen and processes it in one go, significantly reducing computational overhead and speeding up the detection process. We'll now move to the baseline model, which is the faster RCNN. Faster RCNN model integrates a regional proposal network, which is RPN, within its architecture. This innovative setup allows for seamless collaboration between the region proposed network and the main detection network, resulting in even faster and more accurate object detection. Essentially, faster RCNN optimizes both speed and accuracy by delegating and streamlining communication between the components. So faster RCNN consists of three parts. First is the convolutional layers, uh, which uh, which composes of the pooling layers and a component which fully connected to the another extended thing that is used for appropriate tasks like classification or detection. Next is the RPN, region proposed network, which is again a small neural network sliding on the last feature map of inflational layers, predicting the whether or not the object should be surrounded by bounding boxes or not. And thirdly, the classes and bounding boxes prediction. So we got another fully connected neural network that takes input as the region proposed by RPN, and it gives whether it should be a classification, that is the object class, and or the regression, which is the bounding boxes. Here is the visualization of our data set. These are the bounding boxes which detects the vehicles in a traffic scenario. Moving on to the YOLO V8 fine-tune model. So exploring beyond our baseline, which is the faster RCNA, we incorporated an improvement, which is the YOLO version 8 model into our analysis. YOLO V8 offers notable advancement in object detection across various real-world applications. YOLO V8 architecture boasts an updated architecture incorporating an efficient net-based backbone network. This architecture, coupled with innovative features for handling diverse scenarios, positions the version 8 as a formidable tool in object detection. There are many features of YOLO version 8, few of which are the improved accuracy and speed, then updated backbone, as we talked about earlier, a new fusion model that integrates feature from multiple skills, and few data augmentation techniques such as mix-up and cut nets. Here is the YOLO V8 backbone. We can take a look at that. So our model, like in our model, we are using three metrics. Firstly, the intersection over union, IOU, and average precision, and MAP, which is the mean average precision. We'll just go over each one like at a quick glance. So intersection over union is a performance metric used to evaluate the efficiency, the accuracy of annotation, segmentation, and object detection algorithms. It quantifies overlap between the predicted bounding box or annotated region from a dataset. It is a number which ranges from 0 to 1, and an IOU of 0 means there is no overlap between the boxes, and an IOU of 1 means that there is a complete overlap between the two boxes. Similarly, mean average precision, it is a metric used to evaluate object detection model, such as the faster RCN, which is a baseline model, YOLO models, which is the improvement upon that, and a mask RCN, etc., to name a few. The mean of average precision values are again calculated over recall values from 0 to 1. We are focusing on the IOU threshold of 50%. That is the most commonly reported threshold values in most of the research papers. Taking a look at the result, so the culmination of our efforts reveals the promising outcomes. Fine-tuning our faster RCNN model with ResNet pre-trained yielded significant enhancements, which gives a mean average precision value of 5.8 for an IOU value of 50, and a mean average precision value of 3.08 for an IOU value of 75. However, it's noteworthy that YOLO version 8 pre-trained demonstrated superior overall performance with an mean average precision value of 7.93, again on an IOU value of 50, and a MAP value of 6.22 with an intersection over union value of 75. So yeah, these were the results of our pre-trained model. Any questions?
Okay. Um, do you have any explanation why you're seeing this improvement in any of the experiments that you've done?
Uh, Hello. Yeah. So the fine-tuned models obviously have improved performance compared to the pre-trained. So what we did for the pre-trained evaluation was we just took the YOLO V8 pre-trained and the faster RCN and pre-trained models on the COCO dataset. And the COCO dataset has four classes regarding vehicles, like the car, truck, and another two classes, a motorcycle. So we just basically we got the regular prediction. So it gives like 0 to 80, so 0 to 79 because it has 80 classes, the COCO data set. But as for us on fine tuning or our data set, we have just a single class, class 0 for vehicle.
Mhm.
So what we did was we got the direct predictions on our data, and then we just mapped those classes if it was the class label for car or thing to map 0, and then we use that to calculate the metrics for mean average precision. And so as you can see, like it's a much worse performance. I mean, it's around 6% because it has around 80 classes, and a lot of them are not annotated in our data set. So obviously the results are poor, but once we fine tune it and train our model, it learns the weights better, and the classification layer is now just one, that is for the vehicle or not vehicle, background or vehicle. So it performs much better.
Got it. Okay, perfect. Thank you.
Anything else?
I think TA is left.